Can you see the PPT?
Fourier's law of heat conduction. Yes, sir.
Yeah, Fourier law of heat conduction. So, anybody has any difficulty in whatever topics we have covered? What we have covered is just a definition of flux, and then convective flux, molecular flux, and then we have started the molecular flux. And in this molecular flux, we have discussed molecular flux for momentum transfer, which is dealt by Newton's law of viscosity, and similar law in heat transfer, which is dealing molecular flux in heat transfer. Molecular flux is nothing but conduction, where which can be characterized by low bulk motion or no bulk motion, low or no. Okay, so mass transfer, it is very difficult to have the case where there is no bulk motion, because mass is transferring from one place to another place. So that time the molecular flux will be characterized by the less bulk motion, less. But in heat transfer and momentum transfer, same thing will be characterized by the zero bulk motion. So this Fourier law of heat conduction. Then we have solved a couple of one problem in momentum transfer, and this was the problem in heat transfer. So anybody has any difficulty in this? Okay. Today we'll be discussing molecular flux in mass transfer. For simplicity, you can compare, as it is very evident. So understanding conductive heat flux is very, very easy. Understanding conductive heat flux is very, very easy, and mechanism, visualization is very easy. At the same time, it is very difficult to understand conductive momentum flux. Okay, conductive momentum flux, that is what the advantage of this subject transport phenomena is there. So wherever you are comfortable, say if you are comfortable in heat transfer, you take the important information from heat transfer and try to extrapolate this information similar way in momentum transfer or mass transfer. Sometimes you will be very, very comfortable in mass transfer, say for example distillation. So most of the chemical engineer will be very comfortable in discussing distillation. So same logic can be put in heat transfer also. Same logic can be put in momentum transfer also. Only the thing is, first of all, you need to convince yourself. These three subjects are similar to each other. Okay, these three subjects are similar to each other, and so accordingly we can use the information from one area in another area. So with this, so we'll start this fixed law of diffusion. So you can see here also case. Okay, so case is designed in such a way that, so whatever case we have discussed in Newton's law of viscosity and Fourier law of heat conduction, this case in mass transfer is also exactly similar to that. Okay, so only some fundamentals you need to understand actually. So this is mass transfer. So previous was a case of heat transfer. Previous to previous was a case of fluid mechanics. So accordingly, this property will here and there, property will be placed here and there. But logically, this all these three cases look similar. You can see figure also similar. So there is one plate at the bottom. This is one plate at the bottom. There is another plate at the top. Okay, there is another plate at the top, and at t less than 0, and this is filled with some material B. Okay, say you can say A is coated on this plate. A is coated on this plate. So A is coated and this is filled with material B. This is filled with material B, and A is consumed on this plate with some instantaneous fast reaction. As soon as A is reaching upper plate, it is going to 0. So, and this plate is coated with A. Assume that at before start of experiment, this upper layer of this plate is not exposed to B. So everywhere somehow we are stopping A going in B before start of experiment. Before start of experiment, so this Ca will be 0 before start of experiment at time t equals to t less than 0. T less than 0, this Ca will be equals to 0 everywhere from bottom plate to top plate. And now at time t greater or equals to 0, this bottom plate is exposed to B. Bottom plate is exposed to B, so that what will happen? So there will be concentration in first layer of B. This layer is coated with A, and then first layer of B will see some concentration of A. So what? How it will be governed? This concentration Ca0. Ca0 is a concentration here in first layer of B. This is the concentration of A in a mixture of A and B. Now there will be mixture of A and B. So Ca0 is the concentration of A at this interface. This is called as the interface. Interface means this is the first layer of B and last layer of this plate. You can say plate is coated with infinite amount of A. So A is not depleting here on plate, and B, okay, B is there filled in this thing. So at the interface, the concentration is Ca0. Uh, Roll number 99, Siddesh. Roll number 99, Siddesh. Pritish, are you able to hear me?
Yes, sir.
Siddesh. Roll number 51, Himanshu.
Sir,
Yeah. So, do you know any fundamentals what you might have studied previously in some subject? Getting the concentration of A at the interface,
so boundary layer,
boundary
different.
layer. How to get that?
So formula, sir.
Yeah, yeah. So, something will be there, na? Boundary layer means.
Diffusion, sir. Boundary.
Yeah, yeah. So, can you elaborate your statement? Boundary layer means what?
Sir, so the solute part moves from the solvents. High
Yeah,
concentration,
yeah.
low concentration. Okay.
Okay. Consider this. This is the water. Water is filled in a tank.
Yes,
Okay.
sir.
So this is the top surface of the water, and B is say air.
Yes, sir.
B is air, and this is water. Now I want the concentration of A in a mixture of A and B at the interface.
Yes, sir.
So how to get that?
S- Sir, diffusion takes place from air to water.
Huh? Ca0 will be
Ca naught minus Ca. Concentration difference into a mass transfer coefficient, sir. Diffusivity.
oh, that is you are going advanced actually. I'm asking basic, but how to get that Ca0? If say this is the tank filled with water. So here I
Yes,
have tank filled with water and B is air.
yes,
How
sir.
to get the concentration of water at the interface? That is the Ca0.
Sir,
Yeah,
concentration of
anybody
water
else?
is Ca.
Yeah, yeah. Water will diffuse, na?
Yes, sir.
Yeah, yeah. So anybody else?
Hello, sir.
Yeah.
Sir, hello.
Yeah, roll number
Uh, 85.
85. Tell me.
Sir, that concentration Ca naught should be directly proportional to mass of that water column.
No, 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 no.
So
This is
outflow
interface
rate of that,
concentration, Ca naught.
yeah.
So if say you mean to say if tank is bigger, so here Ca naught will be higher. If tank is
No, no, I
smaller,
want to,
Ca naught is lower. This is what you meant to say?
no, sir. I meant if there is more concentration, then more mass will flow out. So therefore,
Yeah,
CA
but
naught is
how
directly
to get
proportional.
this Ca naught? Whether have you studied anything? Because look, studying chemical engineering is not your main aspect. Okay, studying and understanding and using that for your future design and wherever, that is your main aspect. Hence, you are admitted in this VNIT. Okay, so if some fundamental you have studied in the past, you should remember that. Because here I will start with CO naught, but how to get that CA naught?
Hello,
Yes,
sir.
sir.
Yeah, roll number
So 45.
45. Tell me,
So we can use equilibrium relations.
equilibrium. How?
So like Raoult's law and that
Very good, very
Miller's
good.
law.
Raoult's law, you are closer. You are closer actually. So equilibrium means it is assumed that this last layer of water layer and the first layer of air layer. Okay, here first layer of air and last layer of water are in equilibrium. So first layer of water will have a concentrated saturation concentration. Okay, it will have saturation concentration. So that saturation concentration can be obtained by using saturated vapor pressure, psat. Saturated vapor pressure, psat, that will give, okay, total pressure divided by psat, that will give you the concentration here, that will give you concentration, or it is related to psat. So Raoult's law is one of the, you can say, limiting case where you can obtain this. Okay, so using saturated vapor pressure, so saturated vapor pressure you can get this. Okay, ca0, that will be the saturation concentration of water in first layer of air in connection with water. Okay, that will be saturated first layer is over, then thereafter it will, all concentration will be set up by mass transfer actually. But first layer, the concentration in first layer is assumed, it is assumed, or it is observed also, the first layer will be in equilibrium, kind of in equilibrium, and it will have maximum possible concentration of water in air, first layer here, and that maximum possible concentration is Ca0, and that is related with a saturated vapor pressure. Okay, that is related with a saturated vapor pressure. If say now this is solid, say this is NaCl plate. Okay, this is NaCl plate now, and B is water, or this is NaOH plate, NaCl, you can say, assume something. Okay, so this is NaCl plate, solid plate, and it is maintained solid, and this is water. How to get Ca0? Yeah, roll number 45.
So it will be the solubility of salt
Very good, excellent.
at temperature.
If say you have solid liquid case or solid gas case, then that will be a solubility of NaCl in water at a given temperature. So solubility is the maximum possible concentration of A in B. If say A is solid and B is fluid. If A is fluid and B is fluid, then actually uh, it will be governed by saturated vapor pressure of A in B. If say A is solid and B is solid, then A is solid and B is solid, then there will be a negligible mass transfer. So it will be heterogeneous system. It will be kind of heterogeneous system, and there will be a negligible mass transfer in a given direction of mass flux. If A is also solid, B is also solid. So here the concentration is maintained Ca0. Somehow there is an infinite source of A which is given to B, and here at the interface the concentration is maintained at Ca0. Concentration is maintained at Ca0. Now here concentration is highest possible, and as I am moving away here concentration is 0. There is a driving force. Here concentration is 0, here concentration is highest. So certainly there will be a mass flux. Mass will be transported in this direction. Mass will be transported in this direction. And this upper plate, what is happening? So slowly A will diffuse in B, A will diffuse in B, and it will reach a top plate. And now I am selecting A, B and these plates in such a way that there is very fast reaction taking place at the upper plate. There is very fast reaction. As soon as A is reaching upper plate, it is consumed. It is consumed and converted to some other thing other than A and B. So it is converted to P. P doesn't have any role to play with A and B. It is not interfering with A and B. Or it is converted into say P some gas, and it is taken out from this system actually. So here all the time concentration is maintained 0, and here at t greater or equals to 0 all the time, t greater or equals to 0 all the time, concentration is maintained Ca0. So this will be the kind of concentration profile you can expect for this case. This is the kind of concentration profile for t equals to 0. So what is the concentration profile? You can see, you just concentrate on my cursor. This is the concentration profile. This is the concentration profile, vertical and horizontal. So this vertical axis and horizontal axis is nothing but the concentration profile at t equals to 0. Vertical axis and horizontal axis. At t equals to 0, the concentration is Ca0 at y equals to 0. Here concentration is Ca0 at y equals to 0, concentration is Ca0, but everywhere else, because just experiment started, everywhere else concentration is 0. So everywhere else concentration is 0. So this is the concentration profile at t equals to 0. Now as can be seen, here concentration is Ca0, here concentration is 0. So certainly there will be a mass flux or mass transfer in this direction. Mass transfer in upward direction. Mass will be transported in upward direction. So slowly there will be increase in concentration in this region. Increase in concentration in region at time t equals to t1. Say this molecule is diffused till this point. Molecule is diffused till this point. So what is happening? Here concentration is 0. Here concentration is 0. Then slowly this concentration will increase and it will reach to Ca0. Okay, it will reach to Ca0, and I will get this concentration profile. This is the concentration profile. So here concentration is 0, 0, 0, 0, 0, 0, 0 till here, because as A is diffused till this point, thereafter concentration increases. Thereafter concentration increases and will reaches at Ca0 at y equals to 0. This is at time t equals to t1. Then after some time, these molecules are diffused till this point. Molecules are diffused till this point. So only 0 concentration will be in this region, because molecules are diffused till this point, and so concentration will be 0 till this point, and thereafter it will increase, and reaches to Ca0. So this is the concentration profile. So this is the concentration profile. So concentration profile, it is 0, it is 0, it is 0, 0, 0, and then it will increase, and at y equals to 0 it will be Ca0. and these all are transient concentration profile. These all are transient concentration profile. So concentration is changing with time at a location, at a given location. Concentration is changing with the time. So you take this point here. So at time t equals to 0, concentration was 0, and then at time t equals to t1, this was a Ca1. At time t equals to t2, so this was Ca2, and these are all transient concentration profile. So we are not interested in the in this transient concentration profile. So what will happen at steady state? At steady state, there will be a linear concentration variation. Linear concentration variation. So at top plate, concentration will be 0, and at bottom plate, concentration will be Ca0, and there will be linear variation. This linear variation attributes, or because distance is smaller and all mass transport is because of molecular flux. Now here, if you say that, if I am saying that molecular flux or conductive flux is a flux without bulk motion, now these molecules are moving. Molecules are moving. So I cannot say here in mass transfer zero bulk motion, but this bulk motion is very negligible. Okay, flow is very negligible, and what is responsible for this motion is the concentration gradient. It is not a pressure gradient. Okay, there it is not giving rise to a large bulk motion. Okay, low bulk motion. Velocities of a moment, a is moving, molecule a is moving in this direction, a is moving in this direction, but because velocities are very very small, hence this can be categorized into molecular flux, not a convective flux. So in heat transfer and momentum transfer, there was no bulk motion at all in y direction. There was no bulk motion. But in mass transfer, the motion of molecule itself is the property of mass transfer. Molecules are moving from one place to another place. That is why what the mass transfer is there. So I cannot say zero bulk motion. In mass transfer, it is low bulk motion. So it is the duty of chemical engineer now. Chemical engineer is the only engineer which will deal with mass transfer and kinetics. Now you need to decide whether your system is governed by kinetics or your system is governed by mass transfer. How you are going to decide? If this velocity is based on the velocity of the moment, again in mass transfer, whether it is convective mass transfer or molecular mass transfer, so zero bulk motion is not the case in mass transfer. You will not get any mass transfer where you will get a zero bulk motion. If velocities are very very small, then it can be categorized into molecular flux. It can be categorized into conductive flux. If velocities are very very large, then it will be categorized into a convective flux in mass transfer. So this is what the case is similar to previous one, and these are, you can say, this also figure looks similar to previous case. This also figure looks similar to previous case. Only the thing is here concentration is changed. In first case it was velocity, in second case it was temperature, in third case it is concentration. Okay, in third case it is concentration. So certainly, so whatever be the role of velocity in momentum transfer, the same role is played by temperature in heat transfer, and same role is played by concentration in mass transfer. Okay, same role is played by concentration in mass transfer. Anybody has any input related to this? So now viscosity, roll number 42, Rishikesh.
Yes, sir.
Okay, viscosity in momentum transfer is similar to thermal conductivity in heat transfer. Which property plays a similar role in mass transfer?
Diffusivity.
Very good. So here it will be diffusivity. Again, you can see now diffusivity, thermal conductivity is nothing to do with this plate. Okay, I was discussing thermal conductivity of the fluid in between. Okay, thermal conductivity of the solid in between, or viscosity of the fluid in between. It is nothing to do with this plate. But here diffusivity will be a diffusivity of A and B. So likewise, there will be slight difference. Okay, I'm not telling viscosity of water in touch with aluminum, viscosity of water in connection with say steel pipe, viscosity of water in say gold pipe. It was not like that. So similarly, thermal conductivity of copper when it is placed between two aluminum plate, thermal conductivity of copper, it is thermal conductivity of copper. But here diffusivity plays a similar role, but it has both component have contribution. It will be diffusivity of A and B. Okay, it is not diffusivity just merely, it is the diffusivity of A and B. Okay, so under these circumstances, okay, so this case is discussed, this steady state, at steady state, so Fick's observed. Okay, who observed? Fick's observed. So flux, mass flux is proportional to concentration gradient. Okay, so what is observation? Observation is mass flux. Okay, this is rate of mass transfer. Okay, this is ma is a rate of mass transfer per unit area. This is mass flux is proportional to concentration gradient. So here concentration is 0, here concentration is Ca0, here distance is y, here y distance is 0, hence it is Ca0 by y. Okay, so you can say Ca0 minus 0 divided by y minus 0. Okay, so so this is so mass flux is proportional to concentration gradient, and this proportionality constant is a diffusivity, that is the diffusivity of A in B, diffusivity of A in B. If I write, this can be written, okay, this can be written now in mass transfer. You might have seen two unit systems. First one is a molar unit system, another will be the mass unit system. Similarly here also I can have, this is diffusivity of A and B. So similarly I can get a differential form of this equation. Differential form of this equation will be a JAY star. This nomenclature is very important, very important in a sense that these are all standard nomenclature. So for every term in this nomenclature, there is some meaning to that. Here J stands for flux. Okay, flux in mass transfer. This star stands for molar. It is molar flux. A stands for of which component I am discussing the flux, and Y stands for a direction of flux. So this is the mass flux. Okay, flux in mass transfer in molar form, because Ca0 molar form. Okay, Ca0 molar form, A is a component, Y is a direction. That will be minus DAB dCA by dy. Okay, dCA by dy. So this is the diffusivity of A and B. This is the concentration gradient. So negative sign indicates the concentration is decreasing with increasing y. Here y equals to 0, y is increasing and concentration is decreasing. Concentration is decreasing. So you can see highest concentration, decrease, negative slope. This line have a negative slope. So that negative, because of this negative slope of this gradient, negative sign is given here so that I can have this flux positive. Okay, and as I told, there are couple of units, couple of mass transport unit majorly discussed. One will be a molar form, another will be a mass form. So similarly I can discuss for mass form also. So this will be a molar flux. Okay, this will be molar flux, that will be equals to transport property into concentration gradient. So molar flux will be a transport property into concentration gradient. So as can be seen, so this mass is similar to heat, is similar to momentum, then diffusivity is similar to thermal conductivity, is similar to viscosity, then concentration is similar to temperature, is similar to velocity. Okay, but velocity in momentum transfer. So whatever with the role of velocity and momentum transfer, same role is played by concentration in mass transfer. It doesn't mean that velocity is similar to concentration, so you can replace concentration with velocity in mass transfer itself. Velocity has some different role to play in mass transfer. Okay, velocity has some different role to play in mass transfer, but velocity, what is the role of velocity in momentum transfer? When we are discussing molecular flux, same role is played by concentration in mass transfer. Okay, same role is played by concentration in mass transfer. So different form of equation. So this is the so you can see JA star. Okay, so now this Ca can be represented in terms of molar flux, not mole fraction. Xa is a mole fraction. So without thinking anything, when you have small x, so this will be mole fraction into total concentration, mole fraction into total concentration. That will give me a concentration of A. Xa into C is Ca. If total concentration of the system remains constant, so A plus B remains constant for binary system everywhere at steady state, then I can take out this total concentration outside the differential. So this will be a you can say fixed law of diffusion. You might have seen this fixed law of diffusion also. Fixed law of diffusion when in my system the total concentration of system remains constant at steady state, then I can write this form of this thing actually. So similarly I can write in mass form also. You can see this is J star, small j. Small j is also a flux in mass transfer, but this is in mass form. Okay, so this is in mass form. A is a component, y is a direction. So what is the unit of this? This will be a moles per meter square per second. This will be a say gram per not gram, kg. So this will be say kilomole per meter square per second. So this will be a kg per meter square per second. So this will be a mass transport discussed in mass form. So that time I will be discussing this flux with a small g. This is also standard nomenclature. So, so what is the advantage of using standard nomenclature is, so you need not to specify each and everything all the time. As soon as you are writing small j means mass transport discussed in mass form. Capital J star is a mass transport discussed in molar. So this is AY. If you are discussing AY, this will be component and this will be direction. So that will be, this is mass transport, that will be equals to minus DAB. This is the density, variation of density in Y direction. Variation of density of A. Density of A means kg per meter cube. This will be kg per meter cube. This will be moles per meter cube. This Ca, concentration of Ca is moles per meter cube. Concentration of density is kg per meter cube. So variation of density in y direction. So this will be a mass form of mass transport. Okay, this will be a fixed law of diffusion in mass form. Okay, in terms of mass, in mass transfer. So you can elaborate this also. Here I have mole fraction. Similarly, here I will get a weight fraction when total density of the system remains constant. When total density of remain, this is, you can say, a special cases. Special cases when total density of the system remains constant. Total cases, special cases when total concentration of the system remains constant. That time you can write this. Okay, so this will be the equation. So this is also fixed law of diffusion. 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 This is the fixed law of diffusion in molar form. This is the fixed law of diffusion in molar form with total concentration constant. This is the fixed law of diffusion in mass form. This is the fixed law of diffusion in mass form with total density remains constant in for a given system, where DAB is diffusivity. Certainly this magnitude of the DAB depends. Okay, it depends upon this system also. Okay, it will be different actually. So whenever you are using some data book, you should take into account also what is the unit of diffusivity. So that unit of diffusivity, just the magnitude of diffusivity is not important. Unit of diffusivity will give you a hint that whether this diffusivity is diffusivity for mass form or molar form. Certainly, if you are diffusivity in molar form, then accordingly you will get a unit, and that will be given somewhere else. Actually, that will be given somewhere else, that what kind of diffusivity it is studying and all. So what is the special case, whether density remains constant or some, that will be given. So this is the fixed law of diffusion. So now so how many of you convinced that okay, this fixed law of diffusion is similar to Fourier law of heat conduction is similar to Newton's law of viscosity? Just if you are convinced, you can write a yes in chat box. If you are not convinced, you can write a no in chat box. Okay, almost everybody is writing yes. So almost you can say 50% of our transport phenomena is over. 50% of transport phenomena is over. That is what the convincing you that three areas are similar to each other. Now say if you like fluid mechanics very much, you cannot say that I don't like heat transfer or I don't like mass transfer. If you like mass transfer very much, you cannot say that you don't like heat transfer and you don't like fluid mechanics. Okay, say if you say that heat transfer feels I'm feeling very comfortable with heat transfer. Heat transfer looks very easy to me. So it means that all fluid mechanics also easy to you, and as well as mass transfer is also easy to you. Only the thing is logically you need to extrapolate the information. So what is the role of conduction? How conduction can be defined in mass transfer? How conduction can be defined in fluid mechanics? That is what we have seen actually. So slowly we'll expand our analysis to more properties actually. Here just we were discussing conduction. So another name of conduction is molecular flux. So we were discussing molecular flux only, molecular flux in momentum transfer, molecular flux in heat transfer, molecular flux in mass transfer. Slowly we'll increase our attention towards more property, and we'll try to compare the more property in fluid mechanics or momentum transfer, heat transfer, and mass transfer. So so this is what I was discussing. Okay, so there will be here and there something will be there. So dependency of diffusivity on pressure and temperature is quite drastic actually. So in viscosity and thermal conductivity is not so depend on pressure and temperature. So but diffusivity is quite sensitive to pressure and temperature. So many a times the diffusivity, variation of diffusivity and temperature, you need to consider essentially, because sensitivity of diffusivity on pressure and temperature is larger. So that need to be considered. So it is observed that diffusivity is directly proportional to temperature raised to 3 by 2 and inversely proportional to pressure. Okay, so anybody knows? So from which equation we get this information? Diffusivity is directly proportional to temperature raised to 3 by 2 and inversely proportional to pressure. Anybody in a class? The name of the equation? Roll number 78, Deepak. Roll number 78, Deepak. Roll number 83, Ishwari. Deepak.
Yes, sir.
So why you are so late?
Sir, I tried to switch it off, but it turned on and again it went.
Hey, don't tell me now you are expert in this actually. You are expert in giving excuse. I'm not telling online classes. Now tell me, Deepak, what you want to tell? Which
Sir,
equation?
Arrhenius.
Not Arrhenius. Where Arrhenius is coming here? Arrhenius will be in kinetics. Okay, whether have you used this equation anywhere, Deepak? Have you
Hello.
used this equation anywhere? Diffusivity is directly proportional to temperature raised to 3 by 2 and inversely proportional to pressure.
Sir, I guess. Sir, is it Chapman?
Yeah, you don't tell me now equation, whether you have used this equation.
Yes, sir.
Yeah, you might have used hundreds of times. Okay,
Yes, sir.
and you should actually get curiosity itself when you are using this equation. So from where this temperature raised to 3 by 2 is coming, why it is not directly proportional to temperature, why 3 by 2 is coming, why it is inversely proportional to pressure, from where you got the information. So you should get the curiosity, and then you will come to know that which equation is that one. Okay, that we are going to study actually. Anyway, we are going to study. So this diffusivity is directly proportional to temperature raised to 3 by 2 and pressure inversely proportional to pressure. This is very important equation. So as I told, mass transfer is similar to heat transfer is similar to fluid mechanics. So this everybody is convinced, but there are some differences also. So what is the difference? So sensitivity, viscosity is not so sensitive to temperature and pressure. Okay, viscosity is not so sensitive to temperature and pressure. Then thermal conductivity is also, it is sensitive to temperature, but it is not so sensitive. So it is not so sensitive that as soon as you change temperature from by 5 degrees Celsius, thermal conductivity will change. It is not the case. If you change the temperature by say 100 degrees Celsius, then certainly thermal conductivity also will change. But it is not so sensitive. But diffusivity is very sensitive to temperature and pressure. Hence, you will see this equation. You will see this equation which is widely used, because a sensitivity of diffusivity for temperature and pressure is larger as compared to thermal conductivity and viscosity. So even though, so viscosity is similar to thermal conductivity is similar to diffusivity, but they behave differently. This is the diffusivity behavior in mass transfer, that is the thermal conductivity behavior in heat transfer, and that is the viscosity behavior in fluid mechanics. So you need to balance this similarity and differences. Both are important. So just telling that everything is similar, and you will not study fluid mechanics at all, and you will study only heat transfer, that will not solve your purpose actually. You need to study all. Heat transfer also you need to study, mass transfer also you need to study, fluid mechanics also you need to study. This transport phenomena is also important. So transport phenomena will create a balance between these three subjects. So what are the similarity and what are the differences? That is what we are going to study in whole say 30-40 classes in transport phenomena. So this is the temperature and pressure dependency of diffusivity. So this is order of magnitude. These all are interview questions actually. Interview questions. So what is the order of magnitude of diffusivity of compound in gases, diffusivity of compound in liquid, and diffusivity of compound in solid? Order of magnitude. So this order of magnitude in SI unit, meter square per second. So diffusivity is meter square per second. So certainly in solid it is very low. So it is the order of magnitude is 10 raised to minus 10 to 10 raised to minus 14 meters square per second. So this is the order of magnitude. So if somebody is telling me that diffusivity of say nitrogen in gold is 5 into 10 raised to minus 5 meters square per second. So straight away you can say that. So it is not at all possible. Okay, it is not at all possible because in solid, in gold, so whatever compound you take, the diffusivity will be lesser than 10 raised to minus 10. Okay, it will be lesser than 10 raised to minus 10. So when I am discussing diffusivity of any compound in liquid, so it will be in 10 raised to minus 8. Order of magnitude will be 10 raised to minus 8 to 10 raised to minus 9. And certainly in gases, okay, diffusivity of nitrogen in oxygen. Okay, if I am discussing diffusivity of nitrogen in oxygen, and if I am telling that diffusivity of nitrogen in oxygen is 1 into 10 raised to minus 14 meters square per second, so certainly that will be wrong, because this will be order of magnitude. It will be approximately 10 raised to minus 5 order. 10 raised to minus 5 order. So it can be 1 into 10 raised to minus 5 or 5 into 10 raised to minus 5. That's all. So that will be a order of diffusivity of compound in gases, liquid and solid. This is very important. So whenever you are appearing for any interview, so diffusivity, you can say mass transfer and kinetics are the backbone of chemical engineering. Okay, mass transfer and kinetics. Only the chemical engineer dealt with this mass transfer and kinetics. And in that, diffusivity and mass transfer is most important property. Okay, so you should know this. What is the diffusivity of compound in gases? Order of magnitude. If some data is given and whether you want to judge that whether this data is correct or wrong, so at least you can have some input related from this table. So diffusivity of solid, any compound in gases is in order of 10 raised to minus 5. Then it will come a diffusivity of liquid, and if the diffusivity in solid will be lesser than 10 raised to minus 10. So this will be order of magnitude of diffusivity. So we'll try to solve this problem, take down this data and solve the problem. Take down this data and solve the problem. So air at atmospheric pressure. So pressure is atmospheric pressure and 95 degrees Celsius flows at 20 meters square over a flat plate naphthalene. So naphthalene plate is there, 80 centimeter long, in a direction of flow and 60 centimeter wide. 80 by 60 centimeter is there plate. So experimental measurement reports the molar concentration of naphthalene in air, Ca, as a function of distance, as a function of x at a given below. Determine the molar flux of naphthalene from the plate surface under the steady state condition. The diffusivity of naphthalene at 300 Kelvin. 300 Kelvin is 0.6 into 10 raised to minus 5. So you can see, okay, so diffusivity of naphthalene in air. So this is diffusivity of naphthalene in air is 0.62 into 10 raised to minus 5. So order of magnitude of diffusivity of naphthalene in gases. Okay, so it is matching. It is exact value is 0.62 into 10 raised to minus 5 meters square per second. So estimate the molar flux. Roll number 21. Sai.
Yes, sir. Yes, sir.
Yeah. So how to start with this?
Sir, as you given, we have given a diffusivity of naphthalene. It's a 0.62 10 to the power minus 5. And from Fick's law, we have like minus d dCA by dx, which you have derived earlier.
No, that is what you are making a mistake. This is major mistake, because I was telling you so many times. diffusivity is very sensitive to temperature and pressure. So you can see diffusivity is given at 300 Kelvin, and I will be doing the calculation at 95 degrees Celsius. So diffusivity is given at 95 degrees Celsius.
Yes, yes, sir.
Huh?
No, sir, it's given at 300 K, asked at 95 degrees, sir.
Yeah. So what will be 95 degrees Celsius means how many Kelvin? How much Kelvin?
273 plus 95, 8. It's 388, sir.
388. So at 300 Kelvin, diffusivity is given. So you need to estimate the diffusivity at
388 Kelvin, sir. From
388 Kelvin.
Yes,
Yeah,
sir.
from the relation. It is directly proportional to temperature raised to 3 by 2.
Yes, sir.
So estimate the diffusivity at 95 degrees Celsius. And then dCA by dt. How to get dCA by dt? Roll number 44, Narendra.
Sir,
How to get dCA by dt?
sir,
dCA by,
using
not
this,
dt, dCA by dx. This is x is
sir,
given.
using this table, we can easily find it.
Yeah, how can you get?
Taking any two, sir, like a 0 to 10.
Okay, so that is one way. Another way is
We can do with the graph also, sir.
very good. How?
We need to find the slope and we can get
Excellent,
that.
excellent. You will plot CA, okay, CA versus X. First,
Yes,
you will
sir.
plot this CA versus X and draw a tangent at X equals to 0. Draw a tangent at X equals to 0. The slope of the tangent will give you dCA by dx. That is one way. Another way is just you can use this value because this is the nearest value. Okay, nearest value to the surface. So nearest value to the surface is this at x equals to 0 and this at, because I need two values to get dCA by dx. So these are the nearest value to surface. So using this you will get a dCA by dx. It will be negative or positive. dCA by dx will be negative or positive. Roll number 64.
Yes, sir.
It will be negative or positive.
Sir, positive.
dCA by dx.
And it will be negative, and the whole final thing will be positive. dCA by
Oh.
dx is negative.
Yeah, roll number 41 is there in a class. 41, Mithlesh. 41, Mithlesh. Roll number 99.
Yes, sir.
Yes, Siddesh, you are not responding in a class. Okay.
No, sir, my mic was not working at the beginning.
Okay, don't give me any excuses. Whenever I am asking a question, I need your reply. I don't need an excuse. Okay, and at the end, you don't tell me that your grades are going by 1 mark. So this thing, that thing. That time I will not give any excuse. Only the excuse will be your attentiveness in a class was lower. That was the only reason you are likely to get a lesser grade. Okay, so don't give me excuse. I need an answer. That's all. Roll number 78, Deepak. Yeah, same thing with hold good for you also. Don't think that if you keep quiet, and these are online classes, so nothing will happen to uh, your performance. Okay, everything will be counted. I don't know how other subjects are going, but I will make you learn this transport phenomena anyhow. So if you are not interested in learning this transport phenomena, drop this transport phenomena. So, but don't keep quiet. Okay, these three numbers I found quite. Okay, still roll number 41 is not responding. 41. Mithilesh. 41 Mithilesh. Yeah, Pritish, Phaguni, and Saransh. You please inform this roll number 41. Okay, this is not the way what I am handling these online classes, because I cannot see you. I want your attentiveness in terms of this answer, question and answer in a class. Pritesh,
Yes, sir.
yeah, you inform this roll number 41, Mithilesh.
Okay, sir.
Okay. So what is DCA by DX? Roll number 49, Harshavardhan.
It's concentration gradient.
What is the value?
Sir, 1 second, sir.
1 second. So nobody. So I am thinking of giving you assignment now. Writing a class notes. Okay. This is why, because your behavior is, I don't think many people are sitting with pen, paper, and calculator in
So
a class.
0.24.
0.24. What is the value of diffusivity?
So 0.85 into 10 raised to minus 5.
Very good. So concentration gradient is positive or negative?
That will be negative. We will put a extra minus sign to make diffusivity positive.
Yeah, so this is diffusivity, and get the concentration. So this will be a some 0.8 into 10 raised to minus 5. Okay, 0.84 into 10 raised to minus 5. So overall flux will be 2.02 into 10 raised to minus 6 moles per meter square per second. How many of you are getting this answer? Anybody got this answer?
Yes, sir.
Okay, so maybe 2.05, 2.03, or 2.1. That's fine. Okay, order of magnitude should match. Okay, so people are getting these answers. Roll number 60, Aditya.
Yes, sir.
You got this answer, na? So any
Yes, sir.
difficulty? Anybody has any difficulty in this molecular flux in momentum transfer? That is Newton's law of viscosity. Molecular flux in heat transfer, that is fixed law of not fixed, Fourier law of heat conduction. And molecular flux in mass transfer, that is fixed law of diffusion. Fixed law of diffusion. Anybody has any difficulty in this? So any difficulty in designing this case and all? Whether this case, okay?
Excuse me, sir.
Yeah. Can you be a little
Sir,
loud?
85.
Yeah,
Yes,
tell
sir.
me. Yeah, tell me.
Sir, 80.
Yeah, tell
I'm
me.
85.
Yeah, tell me.
Sir, in fixed law of diffusion, we took two plates, and
Uh-huh.
for the lower plate, we considered concentration as Ca naught, and for the
Uh-huh.
upper plate, we considered that there was a reaction going on.
Yeah,
So why did we consider
infinitely
that
fast
reaction?
reaction. Yeah.
Yes, sir. But why couldn't
Why
we take
this?
it as normal diffusion
We
process?
need to equalize the cases. Okay. Somehow these cases are designed similar. 3 cases are
Okay.
designed similar, such that so these 3 areas look similar. So here my main aim is not to discuss this case. My main aim is to compare heat transfer, momentum transfer, and mass transfer.
Sir, but even if we didn't take that infinite reaction, still
Ah.
until the equilibrium is reached, it will satisfy
No.
our equality.
No. If say there is a flux here, so you can say it will never attend. There is continuous A is going here. So somewhere I need to remove A. Similarly, what I have done in momentum transfer is I have kept that plate steady forcefully.
Yes, sir.
Okay, so their velocity I kept 0. Otherwise, if I don't remove this, so certainly this A will be continuously coming here, and if it is not removed, so everywhere at infinitely longer time, everywhere this concentration will be close to Ca0. You will not get
Right,
this
sir.
kind of concentration profile. So you
Got
will
it,
not
sir.
get this kind of concentration profile. So flux will be reducing. Say after say 2 years or so, you will find everywhere concentration is Ca0.
Yes, sir.
So in heat transfer also what we have done, we have removed the heat from this plate and kept the temperature T0 constant. And here temperature was T1. Heat was given here, heat was removed here. In momentum transfer, velocity was given from here, so momentum was given here and momentum was removed. Momentum was removed means I have kept that plate constant. If that was not the case, that is not the case actually. So certainly at steady state, these two plates will be moving with a velocity v. If I'm not keeping this upper plate steady in momentum transfer. Similarly, here also, if I am giving A here, I need to remove A here. So this is the end of the class. If you have next class, you can view the class. So if somebody has questions, can stay back and join the class after that next class. Yeah, got it? So who are
Yes, sir.
84? So
85,
so
sir.
yeah, 85. So just we were trying to design the cases which look similar in all these three area. In turn, my main aim is to compare these three area here. So this is all hypothetical cases. These are all hypothetical cases. So you can say
Yes,
thought
sir.
experiment. These all are
Sir, I had,
thought experiment.
yeah, sir, I had missed that heat removal part from the second plate in Fourier law. That is why I thought what was happening here.
Okay, okay. Now you got
Now I
it?
got it.
Okay.
Yes, sir.
Okay, okay. Anybody else has any questions?
Yes, sir.
Yeah, tell me. Roll
Sir,
number?
in roll number 70, BT18.
Okay, 70. Yeah, yeah, Darshan.
Sir, in the question that we just solved, we had
Uh,
to solve it at steady state, right?
yeah, steady state.
So, sir, so if we use the value of at any x, the
Not
gradient should
any
be
x.
constant.
No, not any x. You should be use the value at closer to surface. So this will be the gradient at closer to surface, assuming that slope at x equals to 0 is similar to this. So either you can use these two values or you draw x versus CA and draw a tangent at x equals to 0. So here you can see I want dCA by dx at x equals to 0
So y at x equal to 0.
because I need a flux at the surface. You can say naphthalene flux from the plate. So plate is at x equals to 0.
Yes, sir. Yes, sir. Okay, sir. It's clear now.
Okay. Thank you. Anybody else?
Hello, sir. Am I
Yeah, tell
audible?
me. Shreyas?
Yeah, sir. In the question we have given that you have given that air flows at 20 meter per second, but there is no significance of that in solving the problem.
Yeah, so this will tell that okay, the concentration, bulk concentration of air remains constant, and that is equals to close to 0. Okay, because velocities are very high, so whatever A is diffusing in air, that is taken away from the plate. So when I go far from the plate, the bulk concentration remains very close to 0. That is what significance of this velocity.
Okay,
Excuse
got
me,
it.
sir.
Yeah, tell me, Rutuja.
Sir, till what limit of velocity we can ignore this bulk flow?
So that we need to calculate actually. We need to calculate the mass flux. If say mass flux are higher, so certainly there will be a convective mass flux also. Okay, but at the surface, yeah.
Yes, sir. Sorry, sir.
So mass fluxes are higher, then we need to take into account convective fluxes also. So that depends upon whole system actually. So that depends upon, you need to calculate Reynolds number and everything. If turbulence is very, very high, that we'll see when we are discussing the estimation of say mass transfer coefficient. So for different cases, you can get different value of mass transfer coefficient, and when to get this mass transfer coefficient, which equation need to be used, that we will be studying when we are discussing mass transfer coefficient or convective flux actually.
Okay, sir.
Okay. So anybody else? Okay, thank you then. See you.